And I think this was saved to YouTube directly. Let's see. Okay. All right. I think we're good to go. All right. So welcome back to today's lecture, which is we have a fire, so that's why we're doing this lecture online. As you can see on the screen, this is today's agenda. But first, an announcement. We're going to have a new classroom in HSS 104 starting next week, if and when we come back. So hopefully it's next Monday. So make sure you go to the new classroom. It's going to be a bigger room, so we all have space there. Last time we talked about classifying differential equations. We did some terminology, we discussed what it means to be a solution, and we discussed what does it mean for a solution to exist on a certain interval, its interval definition. So a solution you can write down, it's not always true, right? But so you have to define on what interval it's actually true for the differential equation. So that's the interval definition. And towards the end, on last Tuesday, I started talking about an example where we can separate the variables, and we use something called the differential form to do that. I wanted to continue with that, sort of a review, and then discuss another type of differential equation called first-order linear equations. And then those are our first two techniques for this week. And then after that, I want to discuss a type of system called autonomous differential equation, where we can plot something called a phase graph and phase line. That's number 3 on the agenda. And lastly, I will talk about what's all on our mind, which is the fire. Okay, and hopefully, so you know, the fire, it is terrible, but then it's also a good learning opportunity. So hopefully you'll get excited about that. Well, I mean, not the actual fire, but the topic, the math part. Okay, so let's start with separable equations, okay? So one, separable equations. So as the name suggests, these are differential equations that can be solved using this method called separation of variables. And so what kind of equations, what do they look like? So they typically have the following form. So in a differential equation, and again, I'll use DE to abbreviate differential equation, is separable if it can be written as the following form. So let's say the function that we're interested in is called y, and the dependent variable is x. Okay, so of course, again, it's not always y in terms of x, but this is just for for our discussion. I would choose y in terms of x. So if you were looking for a function y in terms of x, what does it mean for a differential equation of y that is separable? That means we can write its derivative, y prime of x, is equal to some function, let's say a, purely in x, times another function, b, purely in y. Okay, so any differential equation, a first order differential equation rather, can be written, if you can write it like this, then we say it's separable. Okay, so the derivative is a product of two functions, one purely in x, one purely in y. Okay. So in some sense, the variables are kind of living in different worlds. They're just being multiplied together, not add, multiplied, okay? So why is this interesting is because then we can apply the method of separation of variables. So we can solve these, we can find solutions to these, by this method of separation of variables. By method of separation of variables. Okay, and to do that, the first step is to write it in terms of Leibniz notation. So let's watch this. First, we have y prime of x. In Leibniz notation, this is dy by dx, right? And I know we talked about this is not a fraction, But really, dy and dx themselves later will be some gadget called a differential form. And what that is a thing that can be put into integral. Its job is to be integrated. For now, let's write it like this, dy dx. And if dy dx is equal to a of x times b of y, again, this is kind of review, but we'll see. What we can do is we can cross multiply to move all the y's and all the x's on the same side. Now here is where you might object first. It's like, how can we multiply this dy or this dx? And the reason is because at this stage, dy and dx are actually a new gadget called a differential form. That's a legitimate mathematical object, okay? So here, something dy or something dx, these are called differential forms. It looks very foreign and alien, but then just like the integral sign, the summation sign, it looks alien to you at first, but really you will just, it becomes your friend. Now, what these things are, what these differential forms are, is they are to be integrated. They are to be integrated. That is to say, their only job for them to be meaningful is to be put inside an integral sign, okay? And watch this. Because we have separated the variables, all the y's on one side on the left and all the x's on the right, then we can put down integral signs. Dy by b of y is equal to the integral of a of x dx. Whatever you do to the left, you do to the right, right? And because they're differential forms, they can be inside integrals, so this makes sense, okay? And typically, after this indefinite integral part, there's going to be a constant of integration, so don't forget that constant. That is going to be important. So I'll remind you of constant integration here. All right. So what does that mean? That means if you have a separable equation, you just do this little move, separating all the y's on one side, all the x on one side, integrate, and you're done. Let's see some examples of this. Okay, let's see some examples. The very first example I showed you last week, or not last week, last Tuesday, is this first one. Y prime is equal to y, right? So remember we did this, all right? Let's review this again, and I want to talk about a little bit of detail this time. So again, we're thinking of y as a function of x. Of course, if I give you what the independent variable is, you have to be careful what the names are, but here, let's say y is a function of x. First step, you ask yourself, is this separable? Well, is the function y prime equal to a product of a function of x and a function of y? Yeah, the function of x is just 1, and the function of y is just y. So I can separate the variables. So let's separate the variables. And we say that this is a separable equation. And it's good to be able to recognize it because then you know what to do. So because it's separable, you say, aha, I want to put all the y's on one side after I write dy, y prime as dy dx. So I say I have y dy dx, which is y prime, equals to y. And you separate the variables, you have dy over y is equal to dx, right? So we separated the variables. Now at this stage, you should complain. So what's the complaint over here? Someone should complain about something. We did something kind of sneaky over here. We did what? We divided by y, right? And we don't know what y is. And do you remember, whenever you're dividing by something, you always have to pay attention to, are we dividing by 0, right? So even though this algebraically makes sense that separating y by dividing, we have to kind of pay attention, are we dividing by 0? And so let me make a remark over here. So over here, we're doing this. This assumes y is not equal to 0. Now, what that means is the solution y equal to 0 is something that we may need to revisit later. And in fact, we could have done that in the beginning. So before we do all of this, I'm going to do this in red. I don't know what is red. Is this red? I think so. Before we even start, I'm going to ask you to look for constant solutions. And this will be more apparent later. But what do I mean by a constant solution? Is there a solution that is a constant number, let's say y equals to 5, for example, so that it is a solution to this differential equation? Well, let's think. Let's use the one that I just said, y equals to 5. If y is equal to 5 always, then the derivative of y is 0, but 0 is not equal to 5, so y equals to 5 is not a constant solution. But there is a constant solution, and what is that constant solution in this case? That will be the 0 function, right? Because if y is always 0, its derivative is 0, and it also equal to 0 itself. So here, this problem, it does have a constant solution. It is y equal to 0, okay? And this is kind of nice because the y equal to 0 is the one that we excluded in our separation of variable. So if we didn't do this step, we may have missed a solution, right? So, we have a constant solution, y equal to 0. So we'll just keep this in mind. So later when I say, oh, assume y is not 0, we don't have to worry about that because I already accounted for it here in this first step. Okay, so this is something that's usually good to do before we even start. Find a number that is a constant, and when you plug it in, it actually satisfies your differential equation. This constant solution later will also be called as an equilibrium solution, and we're gonna discuss a little bit more about that as well. And we'll see why that is called this case, equilibrium solution. It's called equilibrium solution because it's always this number. It doesn't change. It's always 0 in this case. Okay. So let's go back to this. Okay. Again, we know what to do next. We have a differential form in terms of y and a differential form in terms of x. So you say, there are differential forms. They are to be integrated. You put integral symbols around them. And then you say on the left-hand side, this is natural log of absolute value of y equals to the integral of 1, which is x. Don't forget the constant integration. Let's call it c like this. Then if we want an explicit solution solving for y as a function of x, we will rescue y by exponentiating both sides. In this case, I get absolute value of y is equal to e to the x plus c, which we're going to do something fancy here because e to the x plus c is e to the x times e to the c. And this is a step where it's going to be an art in this class. You say the letter c here is an arbitrary constant. We don't have any information to determine it just yet. So e to the c is also going to be an arbitrary constant. So this is still equal to some constant times e to the x. Now, you could use a different name. You know, if we're polite people, we would have used a different name called C1. But because we might need to do this relabeling over and over and over again, so long as we know that this is that arbitrary constant, I will reuse the name C here, and then I will just write an exclamation mark over here saying that we abuse the constant. We abuse the letter, the constant C here to sort of, C is now equal to e to the c, basically. Okay, but realistically, it's just another constant, so it doesn't matter what we call it. We can just recycle the name. This is typically a bad thing, but here it's okay. Then you say, okay, we got absolute value of y is c times e to the x. Then what is y? Well, y typically then is equal to plus or minus c e to the x. And again, this plus or minus is a number times an arbitrary constant c, and those combine to be one arbitrary constant. So we again abuse the constant and say this is just c e to the x like this. Okay. So what's the conclusion here is that for this problem, we found first in red a constant solution y equal to 0, that we did that separately. And by our method of separation of variables, we have found a one parameter family of a solution. So here we have y is equal to c e to the x. This is a one parameter family of solution. Okay, so this is still kind of review of what we did. All right, so far so good, yeah? Now, what's interesting about this one parameter family of solution just so happens includes our constant solution. Because if the constant C here is equal to 0, it happens to be the y equal to 0 solution. So this is accidental, right? But typically we shouldn't expect this, okay? Now, why do we call this a family of solution? And that's because for every value of C, there is a solution that will satisfy this differential equation. So what do they look like? Let me draw below. They look like this. I'll do a different color. So if C is positive, then C times e to the x, these are just these exponential curves like this, right? These are all the C is positive solutions. When C is negative, that are these guys down here. It's still exponential, but it's just being flipped across the x-axis. We also have our constant solution, y equal to 0, which happens to be the C equal to 0 solution, and that's fine. We've got them both. We're doubly describing this. So this one right here, this is the C equal to 0, this equilibrium solution. So each of these curves that I just drawn right here, they're all solution to the same differential equation, y prime equals to y, okay? So they are all solutions. These are all solutions to y prime equals to y. And we found it by first looking for constant solution and then applying the method of separation of variables only because it's separable. Okay.
Professor, I have a question.
Yes.
How come there's no constant for ln y? Like, how come?
That's because this integration step right here, so that's not a bad question. It seems like there are two integrals right here, right?
Yeah.
But technically, it's actually one integral. So what's happening actually is this. What you're doing is integral of dy by y plus, minus dx. This is actually what's being done, equal to 0. And this integral has only one total constant. So that's one way to think about it. Another way to think about this is the left integral gives you an arbitrary constant. The right integral gives you another arbitrary constant. Since we do not know what they are, they combine to just one single arbitrary constant. Does that make sense?
So we can just assume that the constants combine together. Okay.
Correct. Because if they're completely arbitrary, then adding them or subtracting them, that is still arbitrary. We still don't know what it is. It's just one unknown thing, right? Now, also, do you guys remember the rule of thumb that I gave last time? Again, this is a fast and hard. This is not a fast and hard rule, but it's like it's a good sanity check. What is the order of this differential equation? What would you say? This is a first order differential equation. And I mentioned that the rule of thumb is if we have a first order differential equation and we don't have any other condition given, just this first order differential equation, we should expect a one parameter family of solution. So this fits our rule. Fits our rule of thumb. Okay. So if it's second order, then we might expect two parameters. But because this is first order, that's how you can sanity check. Hey, we got one constant. Does that make sense? All right. Now you may ask, this is great and all, but how do we know which solution is the one that we're looking for? Well, if this is the problem by itself, y prime equals to y, then that's it. These are all the solutions. These are the solutions. We don't know which one. But if we're given an initial condition, so I would add down over here in red, if we are given further an initial condition, right now just think as just a condition. Let's say, for example, y of 0 is equal to 3, then we can pick out from this family of solution which one is the one that we're looking for. Does that make sense? Right? So then we can figure out which one is the solution to this condition. So if we don't have this condition given, then it's possible that we get a bunch of solutions. But because if we're given this condition, then we may be able to pick out one of them. In this case, if I say y of 0 is equal to 3, this condition right here, maybe this is a number 3 right here. So I should probably label this a little bit. This is y axis, is x-axis. If y at x equal to 0 is equal to 3, then the solution to this differential equation paired with this condition, it is this line, this curve right here. I'll maybe highlight this. Okay, that goes with this condition. Does that make sense to people? Yeah. So that's how we can get one answer, one solution out of this many. Provided that we're given this extra condition, we can pick out which one. Okay. Now, if we pick a initial condition that is negative, then we may be a curve on the bottom. If we pick out an initial condition of 0, then we're this 0 solution, we're this equilibrium solution. So that's kind of interesting. Okay, good. To drive this point in, let me just do another example of separation of variable, okay? And we're gonna revisit this picture later, so have this in mind. So let me show you another example. And again, still simple example, but they illustrate the point.
I'm sorry, Professor, I have a question about the previous one.
Oh, sure, go ahead.
So do we need to explicitly find the constant solution? Because
yes. So if I ask, especially if I ask you to find all the constant solution and all the family of solutions, does that make sense? Yeah. So this is what we're gonna do next is, so you should always make an attempt to find them because they are part of the solution set to this problem.
Yeah, but why I'm asking that is because like it's basically given in this solution, like
it is.
Because we can see that like if c equals 0, then like
that's right.
The constant solution.
So you're not wrong. Oftentimes these constant solution is done by just staring at it. Okay. So, and let me show you another example that will illustrate this point. Okay.
Okay.
So let's take a look at this. Let's say find all the solutions that you can, all solutions that you can. And why am I writing it this way right now? It's because right now you don't know whether that's all the solution, but find as many solutions as you can to this DE right here. Y prime is equal to, it's going to be similar, y times, let's just make it easy, 1 minus y. Okay, I do 2 minus y. I do 2 minus 1. Like that. Find all the solutions that you can to this differential equation. The derivative of y is equal to y times 2 minus y. Again, we're thinking of y as a function of x just for simplicity. All right. First, let's look for a constant solution. So is there a number, magical number, magical constant, so that when y is this constant number always, then we satisfy this differential equation. Now, y constant, when you have a constant function, its derivative is 0, right? So if we're looking for a function of this form, y of x is equal to some constant c, y prime of x is always equal to 0. So this is basically asking us to solve when is 0 equal to y times 2 minus y. And do you see there are several constant solutions in this case? the two constant solution that I can see here is y is always equal to 0 and y is always equal to 2. So we have two constant solution. The constant solution y of x is equal to 0, and the constant solution y of x is always equal to 2. Again, they're constant solutions because their derivatives are always 0, and when we plug it in, we actually satisfy this differential equation. That is to say, this flat line with height 0, that satisfies this differential equation, and the flat line always height 2 also satisfies this differential equation, right? So this is how we look for constant solution, basically setting y prime equal to 0. So far so good, yeah? Okay. Now, let's continue. Then you look at this and say, how can we solve this? How can we find solution? Well, the method that we learned so far is separation of variables. So we're gonna separate the variables and go from there. Now, before we go there, we should ask, is it separable, right? Yep, because y prime is a product of function owing y and a function of x, but that is just 1. So this is separable. Let me write it down here. We have dy by dx is equal to y times 2 minus y. If I separate all the y's on one side, I have dy divided by y times 2 minus y, and that is equal to dx by itself. All the variables are separated. All the x on one side, all the y's on one side. Now, what do we do with this differential forms? Well, they are to be integrated, right? So we integrate both sides. And this is where your Math 8 skill needs to come in, and you need to take some time to review some Math 8. But over here, the left side, we have a rational function in y, which means we can use the method of partial fraction to resolve this integral. So I will do just that. Now, the integral dx, however, that's pretty easy. The integral dx, this thing right here, is 1 times dx, so that is just x plus a constant c. And we're gonna note that this constant c is gonna be absorbed with this constant of the integral with y, so we just need this one constant overall, okay? So let's do partial fraction, or partial fraction decomposition. By partial fraction decomposition, we have 1 over y times 2 minus y is gonna equal to some constant a over y plus b over 2 minus y. I'll just show you how to do this in case you forgot. But this is something I really hope you would review and recall. I'm going to cross multiply to figure out what the numerator is. So the numerator is a times 2 minus y plus by, and that had to equal to the original numerator, which is 1. Now, this is a polynomial in y equal to 1. Now, what does it mean to equal to 1? That means it's equal to 1 plus 0y, no y's. And this gives us 2a minus ay plus by equal to 1 plus 0y. Why am I writing like this? It's because we can match the powers of y to solve for a's and b's. For example, for the constant terms, let me write it in blue, 2a, this has no y's in it, it has to equal to the number 1. So we get 2a is equal to 1. For the terms that have y's in it, that has to equal to the 0y. And I'm going to factor out the y, so this reads minus a plus b is equal to 0. That gives you the 2 equation, 2 unknown situation to solve for a and b. This is not bad to solve. In this case, a is equal to 1/2. And b, if you look at this, b is just equal to a, so b is also equal to 1/2. All right. Continuing our partial fraction decomposition, this means that our integral dy by y times 2 minus y is equal to the integral of 1/2 over y plus 1/2 over 2 minus y dy. And this is not bad to integrate. First, you get 1/2 natural log of absolute value of y, this. And then the next one, because there's a minus sign in front of the y, 2 minus y, don't forget chain rule. We have minus 1/2 natural log of absolute value 2 minus y, like this. And there's a plus c, but we know that this plus c is going to combine with this plus c right here. Let's put everything together. Putting everything together, we get 1/2 natural log of absolute value y minus 1/2 natural log of absolute value 2 minus y equal to x plus c. Again, the c's combined, the constants combined. There's only one parameter here. Now, we probably want to solve for y, so let's try to see if we can combine all of this to solve for y. Using log rules, we can do that. We have 1/2, first the 1/2 factors out. Natural log of absolute value, y divided by 2 minus y is equal to x plus c. Oh, and something I forgot to mention, perhaps I should mention now. Earlier, the first step when we did separation of variable, we divided by y times 2 minus y, right? Here, there's technically a condition that y cannot be 0 and y cannot be 2, but we don't need to worry about that. Those are constant solutions that are accounted for already. So this is great. All right, let's come back to this. Then what do we do here? Well, I could multiply both sides by 2 and watch the power of abusing a constant, all right? If I multiply both sides by 2, I get natural log of absolute value y over 2 minus y equals 2 times x is 2x, but what's 2 times c? 2 times c is arbitrary constant, so 2 times c is just another constant. So if I'm lazy, I will just write it like c. And I again use exclamation mark to denote I abuse the constant. All right. So this is something that you have to get used to. Because otherwise, you could write C1, C2, C3, C4 if you like, if that bothers you what I'm doing, but you're just going to get a lot of C's at the end. Then let me exponentiate both sides. You get y over 2 minus y in absolute value is equal to e to the 2x plus c. Again, abusing the constants, e to the c is just going to be another constant, c e to 2x, like that. Stripping away the absolute value, we can still abuse the constant, like so. And now let me multiply this 2y over, so we have y is equal to, but now this time I have to be careful. Watch this. If I multiply both of that 2 minus y, I get 2c e to the 2x minus y c times e to the 2x, correct? Now, this is an important point. I'm going to make a start over here. Here, you cannot combine, I will say you cannot abuse the 2c into c here. Why not? Well, if we combine the 2c over here into 1c, that means this coefficient is now equal to this coefficient. But they're not the same coefficient. These two coefficients are related. See, one is twice c, and other one is y times c, right? They're related. They're linked together. So in this case, you cannot combine this 2c into one single c. If you do that, the meaning will be completely different. So this you cannot actually combine together as one single c, right? Because the c, we cloned itself, right? We made a clone of it, and now they're tied together. So if you change one of them, you have to change the other. So you cannot combine this 2c into 1c. If you do that, then you need to make the c into c over 2, right? So they're now tied together, so you cannot just put them, massage one but not the other. So you have to leave it like this now. Then let me move the y back. I'm solving for y, right? So I have y times 1 plus c e to the 2x is equal to 2c e to the 2x. Therefore, I get y is equal to 2c e to the 2x divided by 1 plus c e to the 2x. Okay. So as it turns out, without this 2, see, if we had so now that you think, had we got rid of this 2 by combining with the c, then we would have written a different function, c e to the 2x over 1 plus c e to the 2x. They are different functions. One is double the other, right? And that's not quite the same thing, right? So that's what we have. All right, so cannot have this. Let me just erase this. So there we go. This is our family of solution. This is our family of solution.
So Professor, so even though we got rid of the absolute value, it's not plus or minus c times e to the 2x.
Say it again, please.
Since we got rid of, because didn't you in the last one of the other ones, like when you got rid of the absolute value?
The absolute value sign, yeah. The plus and minus got absorbed into the c. That's why I wrote this double exclamation mark to mean I have abused the constant. I have, plus and minus is already merged together with this c right here.
So we don't have to worry about it because the c accounts for it because it's
correct.
Plug in for whatever's okay.
That's right. So maybe I write down that missing step right here. The missing step is y over 2 minus y is equal to plus or minus c e to the 2x. And then I continue to absorb that plus or minus sign into that arbitrary constant c that we don't know what it is. Does that make sense?
Thank you.
So one parameter family of solution. Okay. Now we can do a little bit more about this. You see the top has a c times e to the x, and the bottom have a c times e to the 2x, right? Since e to the 2x is never 0, I could divide top and bottom by e to the 2x. So I could also rewrite this as more succinctly as 2c divided by e to the negative 2x, because I divide 1 divided by e to the 2x, plus c, like that. So all I did here is I divide top and bottom by e to the 2x. This is just kind of, to me, it just looks cleaner. It's just less e to the 2x everywhere. So I write it like this. Okay, great. So what are these things, right? What are these things? Let's plot these out. Now, I'm going to use Desmos to plot these solutions out. So we have our one parameter family of solution, and we also have our two constant solutions right here. So let me write down what we have so far. Oops. So for y prime is equal to y times 2 minus y, we found some constant solutions, y of x always equal to 0, y of x always equal to 2, and y of x equal to this one parameter family of solution, 2c divided by 1 plus c e to 2x for any c. Okay, so we found all of these. I'm going to plot them and we're going to see what they look like, okay? And something interesting will show up, and then I'm going to have to circle back to talk about this.
Professor,
so let me go to.
I think you wrote it wrong.
Oh, did I write it wrong? Oh, why did I write it like this?
Yeah.
Sorry, it's too early. Now, did I correct it? Yep.
Yeah.
Okay. So let me share screen to my browser. Okay. Let's go to Desmos to plot this. I'm going to plot this family out. So let's see, I have y of x is equal to 2c. Now Desmos is smart, it knows that c isn't yet to be determined. It'll ask me to add a slider, which I'm going to do something to that later. e to the negative 2x plus the same constant c. I can hit add slider over here, and I hope you can see on the screen that when c is equal to 1, it is this red curve solution. Do we all see that? Yeah? Now let's try different values of c. Let's try different values of c. If c changes, you see it's changing, the curve kind of changes. Whoa! And now it gives you these solutions, right? So there's a bunch of things that's happening depending on the values of c. What I could do is I can, instead of asking to plot one c at a time, I can give c a list, and then it will plot out a bunch according to this list. So I'm gonna say, maybe go from minus 10 to ... 10. And these are all the solutions according to this family. Now, it looks kind of hard to see, but let me grab an image of this, and then I will summarize what they are. So let me copy this picture. Okay. And go back to my screen. Okay. All right, I have it over here. I'm gonna put it down here. Okay. So the curves that you saw, the family, are these. This is kind of hard to see, so I'm gonna draw larger, a sort of a more symbolic way. Here we have the x-axis. Here we have the y-axis. Do you see that there are these two sort of horizontal lines that is defining some boundary to these solutions? Yeah. They are our constant solutions, in fact. So first I have these red solution right here. All right. This is the y of x equal to 2 solution. And we also have another constant solution down here. That is my y of x always equal to 0 solution. These are my constant solutions, actually. And all these other ones, my family right here, this y of x, depending on the value of c, they look roughly like this. They go like this, and then increase and hug this line, and they increase and hug this line, they increase from here and hug this line, and so on over here as well. And from above, they kind of do this. And from below, they kind of do this. Do you see that? Yeah? Okay. And so you see that there are some various interesting behaviors of these solutions. Some of the solutions eventually have an asymptote of y of x equals to 2. Do you see that? And some of them, the ones, especially the one on the negative, as x increases, they diverge to negative infinity. Yeah? So we have these behavior of these solutions, and they behave differently. And what this means is that since the initial condition is dictating which solution that we're on, depending on our initial condition, we may end up at different places. So for example, if I start over here, if I start over here at point, let me write this as point A. If my initial condition is over there at point A, what's going to happen eventually to my solution? Well, if this is the initial condition following this blue line, eventually it will have a limit approaching 2. Do you see that? If I have an initial condition that starts on top, why does it erase? On top over here, like this, let's call it point B, it will also eventually converge to the value 2. But if I have an initial condition down here, say point C, then eventually it's going to go down like that. So there is some interesting qualitative behavior that we can get just by looking at these plots of all these solutions. So let me make a remark over here. Remark. If, say, and this point is 0, if y of 0 is equal to a, and the value of a is between 0 and 2, is on this interval, then the limit of the solution as x goes to infinity, is going to converge to the value, the number 2, right? That's what happens if we follow this curve. If y of 0 is equal to b, which is strictly bigger than 2, then according to this picture, the limits, the long-term behavior as x goes to infinity of y of x is also equal to 2. And if y of 0 is equal to c, which is less than 0, then what is the long-term behavior here in this case? As x goes to infinity, y of x, by our picture, it seems like it diverges to negative infinity. Okay? So we have this interesting qualitative behavior that we can see right here. Now, then you say, wait a second, what if, let's continue, let's push this point further. What if my point, my initial point, y of 0, is equal to, whoops, is equal to 2 to begin with? What's going to happen? Let's say this is a point D, which equals to 2. What is the eventual limit of the solution? Does anyone want to give me an answer? If it starts at 2, yeah? It's gonna what?
It's
Yeah.
2.
It's gonna stay at 2. This is because 2 is a constant solution, right? It stays at 2. It doesn't change. The limit, well, it's a constant. If y of 0 is equal to, let me make this point E right here. If it starts at 0, then the limit as x goes to infinity, that also stays 0. Again, these are constant solutions. Very interesting. So we have some solution that sort of converge eventually to a number. Some always stay constant, and some diverges. Why should this make sense, right? Why should this make sense? So to make sense of this, I'm going to introduce you to an idea called phase diagram and phase graph, okay? And it's a simple idea, but it's a very powerful qualitative idea, because right now it seems like I had to use Desmos to plot all these solutions to figure out what are these behavior, right? But we don't actually have to do all that. We can use something called a phase diagram or phase graph to figure all of this out. So let me show you that right now. Okay. So we can, in fact, determine these behavior using something called a phase diagram or phase graph. Okay. So I know this is number 4 on the bullet point, but I'm going to talk about this first, and then we take a break. All right, so let's do it. So I think that's point number 3. Phase graph. So to put it in short, a phase graph is just a graph of the derivative of the unknown plotted against the unknown function itself. So this is a graph of y prime versus y, okay? Again, I'm thinking y as a function of x, but x is not we don't care about x here. X is not being plotted here. We want to plot y prime versus y, okay? Now, if our differential equation does not have any x at all, then this graph is very easy to plot. Now, if there is x in it, then the phase graph is not so easy to plot, and we're going to ignore those situations. So the situation of a differential equation where it does not involve the independent variable at all, that it doesn't even show up, is called an autonomous differential equation. And in that case, the graph of y prime versus y is very easy to plot. So let me make this definition first. An autonomous differential equation is one whose independent variable whose independent variable does not show up at all in the differential equation. Okay? So what do I mean by this? So for example, the one that we just looked at, y prime equals to y times 2 minus y. Here, y is a function of x, but if you look at this differential equation, there is no x in it whatsoever, right? There is no x. So this is autonomous. Autonomous. Do you know what autonomous means? Autonomous just means itself, dependent on itself. So this is saying that the rate of change of y only depends on the value of y. As opposed to something that is not autonomous, say y prime is equal to, I don't know, how about x times 2 minus y? This is not autonomous because if we think of y as a function of x here, it depends on x as well as y. Now, why is this an important concept? Because first of all, the phase graph of an autonomous differential equation is very easy to plot. I look at it, I know exactly how to plot y prime versus y. If it's not autonomous, because of the x right there, it's not quite clear what do I plot as a function for y prime. I'll have to figure out what x is in terms of y. So that's not quite easy to deal with. But more importantly, typically, the independent variable is time. So if you have a system that is autonomous, that means the differential equation is independent of time in the sense that it doesn't matter where this differential equation starts. It will evolve the same way. But if you have a system that is not autonomous, then say the independent variable t time is involved, that means this differential equation will behave differently depending on where we start as our starting time. So in some sense, autonomous systems are nicer because they are independent on the starting time. And the non-autonomous one, they will depend on the starting time, the starting x value. Okay. For us, however, autonomous systems, autonomous differential equations have a phase graph that's easy to plot. In this case, easy to plot its phase graph. So I'm going to do that for our example. Let's look at our differential equation, y prime is equal to y times 2 minus y. Again, it's a graph of y prime versus y. So let me draw that. Let me draw it over here. Well, what does it look like? Well, this axis is y prime, this axis is y, okay? This is not the solution graph, okay? It's y prime versus y. So think of y prime as a function f, right? F of y. What kind of graph do we get? So look at this. This is y times 2 minus y. In terms of y, what kind of function is this? What kind of shape is this? Can you tell me? What is the shape? Y?
Quadratic.
It's quadratic, right? It's quadratic. It's a second order polynomial. Is it a happy quadratic or a sad quadratic? Is it happy or sad? It's a sad one. It's an upside down one, right? And in fact, we know there are two roots to this, when y is 0 and y is equal to 2. So I'm going to plot this over here. This is y equal to 0, and here's y equals to 2. It's a sad parabola, so it looks like this. Just go through this 2. Okay, so we have this situation. This is the graph of y prime versus y. Now, what does this mean? Well, this is the meaning. This tells us the sign of the derivative depending on the value of y. Wow, the phase graph tells us the sign of the derivative y prime depending on y, exclamation mark. For example, let's say the value of y currently, suppose you have a function, you have a solution, and at some initial point, its the value is 1. So suppose we start at the number 1 right here. So I'm going to use a little circle right here. Suppose you start at the number 1 right here. Okay, what can we say? So if y initially is equal to 1, what is the sign of its derivative? Well, look at this phase graph. When y is equal to 1, y prime is positive, right? Y prime is positive. If it's positive, what's going to happen to the value of y? The value of y, if the derivative is positive, then is the value going to increase or decrease? It's going to
Increase.
increase. That means if currently the value of y is 1, because the derivative is positive, it's going to want to increase. That means over here, this 1 would like to go to the right. Does that make sense? Oh, interesting. And in fact, we can draw these arrows on each of these segments cut out by this phase graph. For example, if you start to be a number that is negative in our phase graph in this example, y prime is negative, right? You see it's below this horizontal line. That means if you start over here, it's going to want to go to the left. And if you start a number bigger than 2, say 3, it's going to want to also go to the left as well. Congratulations, what you have plotted is something called the phase line. So let me highlight this. This line right here that we just analyzed, that is called the phase line. I know. So the phase line comes from the phase graph. Why is it called phase line? Because it's a line. And on this phase line, we have assigned these arrows, which I'm going to write down again. We have an arrow going this way, we have an arrow going this way, and for an arrow going this way. And we also have 2 interesting points, which is the 0 point and the 2 point right here. Now, what happens at 0 and at 2? Well, at 0 and at 2, the derivatives are 0. It is not moving, right? So those are called equilibrium points. Why am I talking about all of this? Well, remember this picture over here, up here, right? Let me copy this. Oopsie daisy. Oopsie daisy. Let me copy this picture. Okay, make a copy. Oops. I want to make a copy. How do I move it? Okay. All right, move it down here. Move it down here. Let's look at this side by side, okay? This is the picture that we have earlier if you were to plot out these family of solutions and our constant solutions, right? Look at this. Here, if we're at position A, right, look at the is that purple or blue? I have no idea. This dark navy color A, it's a number between 0 and 2. So if it's between 0 and 2, the solution is like to go to the right. It's going to increase all the way to the number 2. And that's what happens to this curve right here. See, it has a limit of 2. You see that? And if we start at a point, so I'll maybe label this not 1, but equal to A right here, like this, it goes to 2. If we start above 2, say at the point B, which I'll make this point B like this, you see, it's going to also come back down and decrease down to 2. See, this describes this behavior. And if it's -1, let's say the point C right here, what's going to happen? It's going to diverge to infinity. And because here the derivative is always negative, starting at C, it stays negative. It always goes to the left. And so that tells us the behavior of all these regions and also these points. Does that make sense? Now, 2 special points of interest is the point D and E. So let's also label them on our picture. Here, by my picture, this is the point E, and 2 is the point D right here. They're kind of special is that at point D's and E's, the solutions don't change. They're constant solutions, right? And they're also called equilibrium solutions, and we can classify these equilibrium solutions. So at y equals, so for y equal to 0 and y equal to 2, these are equilibrium solutions. Meaning that they don't change in time, constant in time. Of course, in X, right? There are constant solutions, but they behave slightly differently. If you look at the solution y equal to 0, the arrows next to it is pointing to the left and to the right, right? So here it has this situation. And for y equals to 2, it has this situation, 2 arrows pointing inwards, you see. So now we're going to introduce a new terminology. If an equilibrium solution has arrows from both sides are both pointing towards it, this is what we call a stable equilibrium. A stable equilibrium. Now, why do you think it's called a stable equilibrium? Well, because in reality, maybe you're designing a building, you're designing the planes of an airplane. Ideally, you want these things to never move ever, right? Let's say you build a building, ideally the building always stands straight, it doesn't move at all. But reality-wise, that is not the case, right? In reality, these things wobble a little bit, right? So even though you made an equilibrium and standing up, it's still perturbing left and right a little bit sometimes. And so now this becomes a problem. Just because we have found an equilibrium solution that ideally it never moves, because of reality, is it sensitive to perturbation? If I were to touch it a little bit, what's going to happen? So for the stable equilibrium, it's an equilibrium that if you were to touch it a little bit, it will come back to that equilibrium point. Does that make sense? So if 2 arrows on the phase line are both pointing towards the equilibrium, then that is a stable equilibrium, because if you were to slightly move to the left, it's going to roll back down, roll back to that point. If you slightly move to the right, it's going to roll back to that point. So that's called stable equilibrium. Anything else is unstable. So this is unstable. It's still an equilibrium point, but it's an unstable equilibrium in the sense that unless you design it so that it always stays as y equal to 0, so it's never moves, then fine, it will stay at y equal to 0. But if I just touch it a little bit to the left, now it's gonna fly up to the left. If I just touch it slightly to the right, it's now gonna fly up to the right. So that's why it's called an unstable equilibrium. Does that make sense? This is a very, very important idea, because eventually, you say you become an engineer, you're building something, finding equilibrium solutions are great because that means your thing is stable and not moving, but not really. Is it a stable equilibrium or unstable equilibrium? Because if you design a building that is an unstable equilibrium, that means touching it will just make it collapse and go the other way unexpectedly.
Professor, does that
Yeah.
mean a stable equilibrium will always be, in real life, will always be in between unstable equilibriums?
Yes, in most cases, I would say, yeah. Because they have to have these arrows that are kind of pointing in the right direction, right? So let me give you another case that we should consider. What about if you have arrows that are pointing in the same direction like this, or like this? Okay. Now, some textbook will define these as, so if you were to propose a name for this, what would you call these? Would you want to call, what name would you like to call them? Are they stable or unstable? What would you like?
Unstable.
Huh?
Unstable.
So these, I'm going to classify them all as unstable. Now, some textbook will call these semi-stable or half-stable. Mathematically, that's fine because on one side it's stable, right? So for example, the first one, if you move to the left, it's gonna go back to this point. But I think that's kind of, in terms of our practical sense, you don't run these anyways because you're not gonna guarantee you're always gonna move to the left only. So because of there is an unstable portion, for our class and for our purposes, we're gonna classify all of these as unstable. Does that make sense? Right. So even if it's semi-stable, half-stable, I don't care about those words. They are unstable to me because realistically, you might go the way that you don't want to. So I don't want to give the false illusion that you think it's stable because there's a possibility that it diverges or goes somewhere else that you don't want it to go. Okay, so we have these 4 cases of stability for these equilibrium points. Okay, good. Okay, so let's take a 10-minute break and we'll resume at 9:22. Okay, so let's take a break till 9:22. And when we return, we're going to talk about another type of differential equation that we can solve called linear first order differential equations. So go stretch and take a break. And I'm going to take a break as well. All right. Hopefully we're all back. Yay. Are we back? Okay. So let me give you some examples of this equilibrium situation before I move on to a linear differential equation. So let me give you an example first, just so we have it. Okay. So, example. Let's consider this differential equation that is autonomous. So consider for y as a function of x, the differential equation y prime is equal to, let's just make it easy, say y plus 1 times y plus 2 times y minus 2, like this. Now, first of all, if I were to ask you to solve for solutions of y, then you will look for these constant solutions, which we can see it. Can you tell what those things are actually? What are the constant solutions over here? Let me just put it in bubble. Here are the constant solutions, which are our equilibrium solutions. They are y is equal to -1, y is equal to -2, and y is equal to 2. Will we all see that? Yeah? Because those are the constant functions whose derivative, of course, are always 0, and when you plug it in, you satisfy 0 equal to 0. Now, some of these are stable equilibriums, and some of them are unstable equilibriums. So let's figure them out. Determine stable and unstable equilibria. Equilibria is the plural for the noun equilibrium. So what we could do is plot its phase graph, right? So let's try to plot its phase graph, which is a graph, again, of y prime versus y. And this is a cubic function, so it's not too bad to plot. The roots are at -1, -2, and also at 2. Let me put it over here, 2. Okay. And because the leading coefficient, y cubed, is positive, we know that eventually it goes like this, right? And it comes back down. It threads this like this. Let me draw better. It comes up and go down like that, right? So this is a cubic function. So hopefully this is something that within your ability. Of course, I didn't draw a very, it's not a very beautiful cubic. I'll give myself a C+ on this cubic, but this is good enough for the purpose. Well, what is the purpose? Well, the purpose is that we can now determine the directionality on the phase line. So along the phase line, which is this y, this is horizontal line, we see that, for example, over here, this rightmost region, the derivative is always positive, so we're going to have an arrow pointing to the right. That. So maybe I use a different color. I'll use this. I don't know what can you see. I use a thicker one. There we go. Right, this points to the right. Now, between -1 and 2, the derivative of y is negative, so we are pointing to the left. Our y is decreasing over there. And from -2 to -1, it's pointing to the right because y prime is positive. And over here is pointing to the left when we're less than -2 because y prime is negative there. So now we have this phase line analysis. We see that 2 is an equilibrium point, but is 2 stable or unstable? What would you say, 2? By looking at this picture, is 2 stable or unstable?
Unstable.
Unstable, very good. 2 is unstable. This 2, unstable. Moving slightly to the left or right of 2 will make it go away from 2. And at 1, is 1 stable or unstable right here? Oh, sorry, at -1. Oops,
Stable.
it's stable. Oops, I keep clicking exit this page. Oops, I lost my line. Oh, I lost the entire curve. Uh-oh. What was it? Like this. Okay. So at 1, -1, this is stable right here. And at -2, that is again unstable. Does that make sense?
I'm not quite sure about how you figure out where the arrow points.
I'm looking at the graph, the phase graph, whether the graph is positive or negative, right? So for example, if you look at this piece right here, this graph right here, that's positive, right? Y prime is positive, right?
Yes.
So if it's positive, that means the rate of change of Y wants to increase. So that's why the interval beneath it has an arrow to the right. It's increasing.
No.
I guess I didn't say explicitly, but our convention is to the right is positive and to the left is negative. Does that make sense?
Yes.
Sorry, I didn't mention that. I probably should mention that earlier. That our convention is the axis to the right is positive, to the left is negative, up is positive, down is negative. Okay?
Yes.
So here we see that this graph of Y prime versus Y is positive. That's why it's pointing to the right. As opposed to the middle part right here, -1 to 2, the graph is negative, right? These are negative. So the phase line will have an arrow pointing to the left. Does that
So
make
you
sense?
you just look at like what's positive and negative, not the
Exactly.
direction.
Yes, exactly. And look at this part. This part is positive, right? So that's
Yes.
what this is going to the right,
Yes.
right? And then again, I forgot what color I use. This part right here, that's negative again, and that's why this part is negative.
Got it. Thank you so much.
Of course. Okay, good. Now also, this can tell us something even more. So let's answer this question right here as well. If we have initial condition, and you can kind of guess what's going to happen. Let's say y of 0 is equal to, let's say equal to 0. All right. So suppose I have initial condition y of 0 equal to 0. What is the eventual behavior as x goes to infinity of y of x? So suppose y is a solution and we start at 0. Y of 0 is 0. What is eventually going to happen to this y value? What do you guys think? So let's look at the picture.
-1.
It's going to flow to -1. Exactly. Right? So y of 0 equal to 0, this 0 right here, I'll use a different color. This 0 right here is right here. And because it's on the phase line pointing to the left, it's going to keep going to the left until it hits something that you can't go beyond, which is -1. So the limit right here is actually going to be -1. Okay. Let's see if this makes sense. What if y of 0 is equal to, I don't know, -3? What is the limit as x going to infinity of y of x? If it starts -3, what's going to happen?
Negative infinity.
Negative infinity, that's right. Because if it starts -3, which is over here, and the phase line is always negative, so I mean the phase graph is always negative there, so it's going to keep decreasing without bound, and it goes over there. So it goes to negative infinity.
Sorry, Professor. How did you get the -1 again?
Look at the phase line right here. So Oh, I can do this. I can do this. Okay. So if we start from 0, right? Can you see the 0? That means our initial condition is right here. And because on this line, the arrow is always to the left, so it's gonna keep going to the left until it hits something. So it's gonna keep going to the left. It's decreasing until it hits over here. That's why it hits -1.
Okay.
And it's actually never gonna hit exactly -1. It's gonna get arbitrarily close to -1. So the limit is gonna be -1 there. So it will just follow this phase line and flow accordingly. So if your initial condition, say, starts over here, say 3, it's just gonna fly off to this direction. And
where's the X then?
X is embedded in Y. X is it's a parameter. This Y value is moving, left and right here. X is sort of like time, as the motion, describing the motion of the value of Y instead. Yeah. So Y of X, say if Y of 0 is here, Y of maybe 1 is over here, Y of 2 is over here, it just keeps moving to the left.
I understand. Thank you.
Yeah. Does that make sense to people? Yeah.
Wait, so Professor, just to clarify, so if it was 1.9, -1,
1.9 right here. Yep.
it would be -1,
It
correct?
will still be -1, correct.
And if it was like -1.9, it would be -1 also, right?
If it's -1 very good, that's just to the right of -2. Because of the space line pointing to the right, it's gonna flow to this point as well. It's gonna flow to -1.
Okay, thank you so much.
That's right. And if it's exactly -1, what's gonna happen? If it's exactly -1,
Is it just going to be
stays
-1?
-1. If it's exactly -2, what happens? Stays -2. Make sense?
Yes, thank you.
Okay. Good. So hopefully that clears up this a little bit. All right. Don't worry, there will be problems for you to try. Okay. Let's move away from this a little bit and let's discuss another type of differential equation that we can solve, that we want to learn how to solve. Let's go over here. This is point number 2. These are first order linear ODEs. Okay. So if you think about the classification that we did last time, first order, that means the highest derivative is 1. We're still really just doing first order so far, at least for this first midterm, unless there's a trick to deal with it. But right now, we're really mainly dealing with first order right now. But what about the word linear? So let me recall for you, what does that mean? So remember the definition, it's a linear combination of the derivatives of y. So for y as an unknown function of x, okay, a first order linear ODE looks like this. Okay, let me write it down. Some parameter function a1 of x times y prime, y prime really is a y prime of x really, plus a of 0 of x times y of x equal to some forcing term f of x, right? So remember, first order linear ODEs, they all look like this. It's a linear combination of the derivatives of y with coefficients, some functions of x, and then perhaps there is a f of x term. Sometimes this is the, in physics you call it, or in engineering you call this the forcing term. This is the forcing term. The reason is because this is usually some external force that you add to the system. But in math, especially if you have taken linear algebra, this is actually also known as the non-homogeneity term. And we say a linear ODE is homogeneous if that forcing term is 0, just kind of like homogeneous system of equation when it's all equal to 0 or not equal to 0, that's all. Okay, so these are just some nice notation to sort of refer to this term, the term that has no y's attached to it. Okay, what we like to do right now is to find a method of solving all of these first order linear ODEs. Okay, so let's do it. Now, to do that, something is kind of messing us up because there is a1 of x right here. This term is actually going to be annoying to us because it could be a function that's sometimes 0. So because I don't want to deal with that case right now, I want to deal with a special form called monic form. So let us deal with monic forms first. And the rest we have to kind of read between the lines and see if dividing by a1 of x is gonna give us a trouble. So what do I mean by monic form? Monic, meaning the number 1, means the leading coefficient is 1. So I'm going to have a differential equation that looks like this. Y prime of x plus, and because a0, I don't want to keep using a, I'm going to write maybe something like p of x, y of x is equal to some q of x. So imagine I divided a1 of x, so I have this form, okay? Now, whether dividing a1 of x is gonna give us some trouble, we will sort of shove that under the rug right now. But let's focus on these monic forms, and we like to develop a tool, a method to solve all of this once and for all. We will develop a method to solve all of these. Wow, that's a big claim. So we're gonna solve every differential equation that looked like this monic linear first order ODE. Are you ready? Okay, that's our task. How do we do this? How do we do this? Well, if you look at this monic form, we got y prime and we got y, right? And the y is multiplied to something else. And they're being added together. So in your experience in calculus, let's see if you can make this connection. Have you ever seen some function added to its derivative at some point? So I'm going to use a cloud to draw this. Have you ever seen a sum of a function with its derivative ever? Think about it.
Yes, in physics.
In physics, okay. But in math, is there a calculus situation where you have a sum that involves the function and its derivative?
Sine and cosine?
Sine and cosine, okay. Well, what about this? The product rule. So look at this. Look at this. In light blue, suppose we have two functions, f and g, and I take the derivative of their product. Again, f and g thought as functions of x, okay? For example, if I take the derivative of f times g, what do we get? Well, we get f prime g plus fg prime, right? Here's a situation where we see both the function f prime, I guess I want to highlight this. We both see f prime and f together and being added together, right? Here we have y prime and we have y. So this looks kind of like a product rule situation. So again, remember, what is our goal? Our goal is we're going to find a solution to this type of differential equation. All right. So I'm going to insert that idea into your head that there is some product rule looking thing going on. Now, why do we care about this? Well, let's think. Notice, if we don't have the p of x term, if we don't have the p of x term, so we just have y prime is equal to q of x. Can we solve this? How do we solve y prime equals to q of x? How would you solve that? Do we have the technology?
FTC?
FTC, we just integrate, right? Exactly. So very important observation. If we do not have the P of X term, our problem is y prime equals to Q of X, which can be solved by FTC. Be solved by FTC, exclamation mark. But because we have this term right here, that's gonna make FTC not easy to apply. So we want to massage it so we can apply FTC. So what we want to do is this. We want to modify it so we can apply FTC. Okay? How do we do this? Well, look, it's very similar to this product rule situation, but y prime is missing something in front of it. So here we go. This is what we're going to do. Suppose we have another function. There is some function. Let me call this mu of x. This is the Greek letter mu, or it's the letter M in Greek. Or if you actually, do people actually speak Greek here? The Greeks do not pronounce this letter mu. This is the mathematical English way of pronouncing the letter mu. In Greek, this letter is pronounced mi, but we're gonna pronounce mu. Okay. Suppose there is some function called mu of x. All right. Let's multiply to this whole thing. To our differential equation. Now, presumably, this mu hopefully is not zero, so multiplying it does nothing interesting. So we have mu of x times y prime of x plus mu of x, p of x, y of x is equal to mu of x, q of x. Okay? So we're wishing for some function mu of x. Okay? And what do we wish is that, well, we wish that if we were to multiply to our differential equation, so that this left-hand side turning into the derivative of mu of x times y of x. So we wish this happens. We wish the left-hand side is actually just the derivative of mu of x times y of x. Okay? We wish this to happen. If our wish is true, so we wish this mu y prime plus mu py is equal to quantity mu y prime. I know it looks kind of weird. Hopefully my writing is clear enough. We wish this is true. If so, what does that mean? That means we have mu times y prime, quantity prime, is equal to mu q, right? What does that mean? How do we undo this derivative right here? We have the derivative of something is equal to mu q. So what can we do? We can use the derivative of something is mu q. So how do we solve for
integration? FTC?
FTC, exactly. We can do FTC. By FTC, mu y is just equal to the integral of mu q. Okay. So this is interesting. Let me say it again. We have some unknown function mu, and suppose that when I multiply my unknown function mu to our differential equation, the left-hand side magically, we wish that to happen. Suppose the left-hand side magically turns into the derivative of mu times y. Then we can just apply FTC to get mu y is equal to the integral of mu q. Now, because integral mu q as a constant, I'm going to remind you by writing that there's a constant of integration by writing it over here, plus c here. Then the function y is clear. The function y is just 1 over mu times the quantity, the integral of mu q plus a constant c. We have solved it. Ta-da, that's the answer. So all we need is a magical function mu that satisfies our wish. And if our wish is satisfied, we can write down the answer directly. The answer is just 1 over mu times this integral mu q plus a constant c. Okay? So how can we make this wish come true? So let's see. Let's look at our wish. This is our wish. Let's make our wish come true. Let us make our wish come true. Let's see what do we need to make our wish come true. Well, we wish for Christmas mu y prime plus mu py is equal to the derivative of mu y quantity prime, right? Well, by product rule, mu y quantity prime is mu prime y plus mu y prime. Stare at these equations very carefully. On the left, we got a mu y prime. On the right, we also got a mu y prime. You see that? So that means we need mu py is equal to mu prime y. Well, both sides got a y, and so what this means, our wish will come true if mu p is equal to mu prime. In other words, we want mu prime over mu is equal to p. So let's backtrack a little bit. We're deriving the method, and what we saw is this. If there's a magical function mu, and such that this magical function mu satisfies mu prime over mu is p, then the solution is y is equal to all of this. Let me put it in a box and write it as a method. Let me summarize. Method. Okay. For the monic linear differential equation of first order, for y prime plus py, I'll write p of x because we need to know the variable name. For y prime of x plus p of x, y of x equals to q of x, you first find this mu function. Let mu of x be such that mu prime of x over mu of x is equal to p of x. Then the solution y of x is simple. It is just 1 over mu times the integral of mu q plus a constant, all being multiplied by 1 over mu. That's our method. And that's kind of cool. So whenever we see this monic form, all we need to do is find out this magical mu and plug it in, and we get the answer. But we can do something better. Look at the condition of mu. The condition of mu is itself a what? This condition, this is a what? What kind of equation is this? What kind of equation? This is also a differential equation, right? What's the order of this differential equation?
1.
First order. Is it separable?
Yes.
It's separable. You see, this part right here, it says the following. This part says d mu by dx over mu is equal to p of x. So we have d mu over mu is equal to p of x dx. It is separable. By integrating both sides, we get that natural log of absolute value of mu. I think we all know this step very well. Is equal to the integral of p of x dx. There is a constant of integration, so I'm going to write it out plus c right here. And if we undo everything, you're going to derive that mu of x is equal to c e to the integral p of x dx. That's what mu is. Now, before we move on, this c right here is not the same c here. There are different c's. These are not the same c's. And I claim this c right here, it's not necessary. Why is it unnecessary? Because this c right here, if you follow the c, it's going to show up in this mu, and it's also going to show up in this mu down here. So those c's are going to cancel each other out because it's just a constant. Those two constants are going to cancel each other out. So what we can do is not write the c. And that will reduce our complexity of our equation because then you won't get confused about that c versus the c right here. So I'm going to rewrite our method to be the following. And this is the one that you could just memorize if you like, but what I showed you is the derivation. You set mu of x simply equal to e to the integral of p of x dx. Then the solution, magically, y of x is just equal to 1 over mu of x times the quantity of mu of x, q of x, dx plus c. That's it. This is provided that our differential equation is this monic first order form. If you have a monic first order differential equation and then it's linear that looks like this, then the solution is just given by this formula, if you will. Isn't that nice?
So,
Yeah.
Professor,
Mhm.
how did you get the C on the right side, the unnecessary C?
The C right here?
Yeah, how did I,
That's
how
C
does that?
because here there's a C right here, right? There's a constant C. And when I exponentiate both sides, it's gonna give you like e to the C here, and that's a constant. Does that make sense?
Oh,
Right? That's what the C is. Okay, maybe let me write them step by step, right? If I exponentiate, this is gonna be this plus C, right? Do you see that? And that e to the C is gonna be e to the integral px dx. This is the same situation as before, e to the C like that. And that's the constant that I was talking about. That's not necessary.
I see. Thank you.
Okay. This constant is not necessary. Again, it's because it's going to show up here in the mu and show up on the downstairs in the mu, and they are going to cancel. So I'm just going to write this will get canceled anyway. So no need this term. But very importantly, I hope you all didn't miss this. This C, however, over here, that is not optional. You must have a C here. That term is very important because that term C is gonna get multiplied to this 1 over mu right here. So you cannot miss that constant C. This constant cannot be missed. This is important. Okay. Of course, after doing the antiderivative, you're gonna get a C. I'm writing the C preemptively here to remind you there's gonna be a constant C there. Okay, that's gonna be our one parameter for our one parameter family of solution. Okay, let's apply this. So maybe copy this down on a separate sheet of paper. We're gonna just apply this to see how this could solve a problem. Watch. So example. Okay. Find a one parameter family of solutions to this differential equation. Y prime is equal to y plus x. And again, the function y is a function of x. This differential equation, what is the order? What's the order?
First.
First order. Is it separable? Is it separable? Is y prime equals to the product of something in x times something in y only?
No.
It's not separable. So the method of separation variable fails, but it is linear. Linear, not separable. So we can apply the method that we just developed right here. First, I'm going to write it in this mnemonic form. Y prime plus something times y equal to something in x. So let me do that. Y prime minus y equal to x. Okay, now stare at this equation and maybe I zoom in. Okay, if you look at these, what is P and what is Q right here? Can you tell?
Q is X.
Q of x, this is Q right here, right? Q of x is x. What about P of x?
Is negative
Is
1.
1.
Negative
Negative
1.
1.
Negative 1, right? All right. Now, this box is the magical box because this is saying that just follow this box and pop, the answer comes out. So how do we use this box? It says, first find this mu. So by this box, it says, well, calculate what mu of x is. It is equal to e to the integral of p of x dx. Okay. P of x is minus 1, so this is integrating negative 1 dx in the exponent of e, which is e to the negative x. Now, there would be a plus c, but I just said this plus c is not necessary for mu. So we don't need any c's here. Done. We got the mu. And continuing with this magical box, which we derived, by the way, but that's the joy. We derived it so we can use it. It's saying that the answer y of x is simply 1 over mu of x, whatever mu we just found, times bracket integral mu of x times q of x dx, and don't forget the plus c, which is important here. That plus c is gonna give us the one parameter family. Let's plug everything in. So now it's just a calculation. 1 over mu of x is, of course, e to the x times bracket integral e to the minus x. Q of x is x dx, and the plus c is to remind you, don't forget the plus c. Here, you're going to encounter this integral. Now we have finally did the differential equation. How do we solve this integral? Do you remember?
By parts.
Integration by parts. So again, I hope you will go and review. You want to treat this class as an opportunity for you to review Math 8. It's kind of forcing you to review Math 8. That's sort of secretly part of my goal as well, because you took Math 8 and this is the celebration, a victory lap here. So I'm going to do by parts. I don't know how you do by parts. I'm just going to do by parts my way. So I know that e to the minus x is the derivative of negative e to the minus x. And by parts, I know that integral u dv is equal to uv minus integral v du. So I have my u dv here. So uv, that's minus x e to the minus x minus integral minus e to the minus x dx. Again, I don't care how you do by parts. You can do tabulation. I don't know what you learned. Just do by parts. This equals to minus x e to the minus x plus, but the antiderivative e to the minus x gives you another minus sign. So that's minus e to the minus x plus c. Okay, so that's the final result of this by parts. So if this is very magical, please make sure you review this. So let me fill that in. E to the x minus x e to the minus x minus e to the minus x plus c. Okay, the plus c is to remind me that I need this plus c. So finally, the answer is, by distributing this e to the x, we see that e to the x and e to the minus x cancel. So that's minus x minus 1 plus c e to the x. There we go. That's y of x. Ta-da. Now, at this moment, you may say, okay, once we have done the integration correctly, we have obtained this answer. Is this answer right? How would I check whether this answer that we got is correct? What would you do?
Take derivative.
Plug it back.
Plug it back in. Let's plug it back in just to double check, right? Because we use a magical box, right? And sometimes it's very magical that a box just magically happened to give us the answer. So let's plug it back in to see if this truly gives us y prime equals y plus x. So let's check. Just for our sanity. So y prime of x, so is y prime of x equals to y of x plus x, y plus x, question mark? The derivative of y, the left-hand side, is just minus 1 plus c e to the x. That's it. The right-hand side is the y function, which is minus x minus 1 plus c e to the x plus x, which the minus x and x cancel, giving us minus 1 plus c e to the x. Wow. I hope you all got a wow. Is it a wow? Wow, it works. Again, it's not really that magical. It's because we made it so this happens. Wow, thank you for the wow. Exactly, right? So all this works because we found this magical mu. This magical mu has a name. The name of this mu is called an integrating factor. This magical mu of x is called an integrating factor. Now, let's think about what was the role of this magical mu. Let me scroll back up a little bit. Remember, in the very beginning, when we started with this monic form, we said that, hey, this p of x term, that's giving us some trouble. If that term is not there, then we could have done FTC directly. But because it's there, we can't do FTC. However, if we multiply this magical integrating factor mu, suddenly that enables FTC to work directly. So the purpose of this integrating factor is allow you to solve the problem by integrating at the end. That's why it's called integrating factor. It's a term where after multiplying it, allows you to find the answer by a simple integration. So this integrating factor allows solution to be found by integrating. That's all. Okay. But it does have a derivation, which I will ask you to review how we got there. But once we had derived it, the procedure is always the same. When we see this monic first order linear differential equation, you find this integrating factor. This is the integrating factor. And once you have found this integrating factor, you can just write down the answer. Of course, writing down the answer may involve actually performing some integration, say by parts in this case. But once you have done all that, you have gotten the answer. You have got our one parameter family of solutions. Does that make sense? Okay. So I'll have some homework question for you to try on these. Now, since we're already at 10:06, 10:05, our normal lecture time is over. So if you'd like to leave, you can. But because yesterday we didn't have a lecture, I do want to talk about something interesting. And if you look at our agenda, there is the fire. So I do want to talk about the fire and see how that might relate to everything that we just learned. So if you'd like to stick around, I'm going to continue to talk about the fire. But before we do that, we will take another 10-minute break. Is that okay with people? Yeah. So again, this is all recorded, so you can find all of this.
How long
But-
does it take, Professor?
Hmm?
How long does it take? Around?
It's probably gonna take maybe 30 minutes to an hour.
Oh,
I don't
okay.
know. Yeah. So if you'd like to stick around, I will talk about the fire at 10:15. Let's take a shorter break. Okay.
Professor,
Yep.
just tiny questions about
Yes.
the last page, the first line, the writing in red.
Mm-hmm. Where?
Yeah, right there. The writing in red, a little above yours. Yeah.
Yeah.
Here it says mu x equals to e to the integral px equals e to the integral minus dx,
Yeah.
which is e to the minus x. Shouldn't it include the constant on the power of the e?
Right. So again, this integrating factor part, you don't need a constant. That's what I was talking about over here. For the integrating factor, this constant on top, you don't need it because later it's gonna get canceled out in the final form.
Oh,
Because if there's a constant that comes out over here, that constant is gonna cancel top and bottom right here. So we don't need to write that in. Does that make sense?
okay.
So no need constant for the integrating factor here.
Are you gonna post the recordings in Canvas, right?
Yep, I will. But the later step, this constant is needed, okay? But for the integrating factor, you do not need the constant. Sound good?
Yeah.
Okay. And again, it's because they will get canceled out. They will get canceled out later. So to spare you the confusion of these two different constants, it's just fortunate that this constant in the integrating factor is unnecessary. That's why.
Can I copy the last page?
Yes.
Another question that I have is that how did you get y prime of x? Like, do you just differentiate the y of x that we found?
Yeah, exactly. I just differentiated this, right?
Yes.
We're checking the answer because we're claiming that this is the solution to the differential equation y prime equals to y of x plus x. So the left side is y prime. So I use the answer that we got. We say, all right, I claim y is this. So let's take the derivative. We got -1 plus c e to the x.
Another thing that you talk about partial fraction is that, wait, was there like a cover-up method that we learned in Method 8 instead of like distributing everything?
Oh, you can use the cover-up method. That's perfectly fine as well. Yes.
But I kind of forgot how to use that.
Oh,
Like, do
then
I
you should look it up. Okay.
cover-up method?
Yeah. So go look it up. But the
Thank you.
cover-up method only works if there is no like repeated powers actually, right? So, or you can plug in values as well. There's also a substituting values. I'm going to leave that to you for you to discover. But yes, you can use whatever method you like. Okay.
But what would you suggest though for this course to just simply like distribute it or?
Can I give you an answer that is very disappointing? The answer
I
is
already know the answer. It's fine.
the answer is the more methods, the more different methods that you know to solve the same problem, the more powerful you will be. Does that make sense? So there are times where the cover-up method will be very useful. So maybe later I'll do a different one in class where I use different method to solve the partial fraction. But you also should want to be able to solve it algebraically like how I did. That's the most basic way of solving these. So have you seen this being solved algebraically like this before? Yeah.
Yes.
Yeah. So this is the basic method. At the very least, you need to be able to do this. Because if you forgot your other method, at least you can do this method. Okay?
Thank you.
Other ones are called tricks, and tricks are useful in special cases. So here there are several ways. For example, you can plug in A is equal to 2 and get B directly, right? So if I can plug in Y is equal to 2, right? So for
Yes.
example, over here, you can say plug Y is equal to 2. If I plug Y is equal to 2, then what do we get? We get 0 plus 2B is equal to 1. So immediately B is equal to 1/2, right? So there's a plug number method. And we can plug Y is equal to 0. If I plug Y equal to 0, then we get A times 2 is equal to 1. That also gives us A is equal to 1/2. Make
Yes.
sense?
Yes.
So the more method that you know to solve the same problem, the better it is, because you have to eventually sort of get a sense of when is it going to be useful. And one method may be useful sometimes, maybe sometimes not.
Yes.
Okay.
Thank you.
So at
Professor,
10:15, I want to talk about the fire. Any other questions? Yeah.
Professor, are we expected to derive the integrating factor on the exam?
No, you can just memorize this box if you like.
I see.
Yeah, but it's just that you do want to know the steps of how you get there. So try your best to understand it. But if on a test you just say, well, you recognize this is a first order linear monic form, you apply this magic box which you memorized, then fine, more power to you. I don't mind. Okay.
I see. Thank you.
Unless I'm so mean, I said, okay, derive it.
Oh.
But I think I won't do it, maybe. So for now, learn it, but for sure, know that there is this box. Is that okay? Yeah? Yeah.
Is the exam gonna be like the homework questions that we're doing right now?
Right, exactly. Yeah.
Professor, another question.
Yes.
Are we gonna get any practice exams or like previous exams to get an idea what part of
So the practice that for the exam is really all the homework questions. So I'm just gonna say that much. If you have honestly done every homework question, you have prepared for the exam.
Okay, sounds good.
Okay. Yeah.
Professor, do we have office hour today or tomorrow?
Okay, I can have office hours tomorrow.
Oh, perfect.
Yeah, so since we haven't been having office hours, let's also have it online on Zoom, okay? How about that?
Yes, perfect.
Yeah.
Perfect, Professor, because we
Yeah,
have
and can we have it, should we have it at 8 or at 10? Or let's see, what's a better
it's
time?
whatever works for you, it works for me as well.
I want to start at 8, okay, because I
At
want to.
8, okay.
And
Okay.
so let's have office hours at 8. And again, I will also, because it's online, I will record it and then I'll put that online as well.
Oh, okay, perfect. Thank you.
Okay, so I'll send an email about that. And I think at 10, Joanie will have her office hours as well, right? Is that true, Joanie? Is she still here? Is Joanie here?
Yeah.
Yeah.
Or maybe just email me or send me the Canvas message or something.
Okay, yeah. So Joanie will send out her times as well for her, also Zoom on Friday.
Oh, okay, thank you.
Okay. All right. It's 10:15. Should we talk about the fire? Let's talk about the fire. And this section will be kind of an application of everything that we have done so far. All right. So let's talk about the fire. I don't know if this is yellow. All right. So I don't know if you have been paying attention to the news. So the fire started. Do you remember when did the fire start? Did people remember when did the fire started?
When or where?
Oh, when? What time? Do you remember? Roughly what time?
3 days ago.
Right, on Tuesday, right? About noontime, right? So the fire started on Tuesday noontime. And last night, I don't know if you checked the news, the amount, let's just focus on the Palisades fire right now. It has burned 10,000 plus 15,000 acres. It's insane, right? The amount of fire, the amount of area that the fire covered, it's so huge. How did it get there, right? So I want to propose a model to sort of study this phenomenon. Now, just as a warning, I'm going to give you a very simplified model. Of course, true fire dynamics and modeling is very, very complicated and very, people need to study this in much more detail. But even with our children differential equation, I keep calling this class children differential equation, we can get a very good sense of what's going to happen. Okay, so the first instance of the fire, again, we're focused on the Palisades fire right now. There's so many that's happening. The fire first started, I would say, around, it's like maybe 10 to 11. Let's just say noontime. Let's just say noontime, around noon. Okay, probably earlier, but then by noon, there's fire already. Okay, and let's see how much fire there was. So let me share, let me go to website. Let's go to LAFD. Okay. I believe LAFD tells us what happened with the fire. More news, Sunset Fire. I want to look at the Palisade Fire. Okay, let's look at the Palisade Fire. This is the official website, right? I'm just at the official website of Los Angeles Fire Department. So it has some chronicles of what's happening. This is up to yesterday. I think they stopped updating because it's just very depressing or something. But let's keep going. Let's go as far back as we can, right here. So around noontime, Tuesday, there's already 200 acres burned. So around Tuesday noontime, I'm just writing this down. It's about 200 acres already burned. Okay. And let's keep going. The next moment is right here at 1:40. It is now 300. Do you all see that? Yeah. Now 1:40, I'm going to round up to 2 p.m. I don't want to, there's too many decimals. So 2 p.m., roughly 2 p.m., say 300 acres. All right. I'm just writing down on my note. And then what happened? So we started at 200, right? Noontime, 200, 2 hours later, 300. And then if you look at a little bit more later, let's say later that night, at 7 p.m., 3,000 acres. You see that? And then the next day, maybe 24 hours later, next morning, so yesterday morning, still about this 2,000. I don't know how good is this estimate, but come forward one day, one full day. This is 12 noon the next day. 12 noon next day. 12 noon Wednesday. It is 10,000 acres. Isn't that crazy, right? So the number blew up, right? It blew up. So what I want to do right now is to give a simplified toy model to model how much acre are we burning, okay, as a function of time. So that's what we want to do. We want to model this thing, and that will give us a sense of what's happening. Okay. So
with considering the wind or without wind?
Without any of that, okay? So without the wind, just like if it just burns by itself, right? And there is no firefighting efforts, there is no wind, just the fire spreading by itself, what will happen? Sort of the most basic situation. Again, whenever you're studying a problem, you want to start as simple as possible, and then we slowly add complication to see if we can. Make sense? Okay. So let me go to my notes right here.
I'm sorry, Professor, but if we assume that the fire will burn no matter what, then it will go to infinity, I guess.
Okay. So we're gonna need to have a model that have an upper bound. So let me show you what that means, okay? So I'm going to propose a toy model. Again, by no means should you ever use this to do, if this is reality, this is sort of our back of our envelope calculation. Does that make sense? So I'm sitting here, looking at the news, and I just like did some calculation. I go, this number roughly makes sense. That's sort of calculation. That's what we're doing. Does that make sense? Yeah. Sort of our first approximation to the problem. So I'm going to propose a model. It's a toy model, meaning that it doesn't necessarily have to represent the actual, all the reality all at once. But this model is actually very powerful. So let us write, I don't know, let's say y of t to be the acreage, basically area burned on fire. I'll just say area on fire. Okay, as a function of time. And time t is going to be measured in hours, and area is going to be measured in acres. Okay, so y of t is this function. So a simple model to model this is the rate of change of y as a function with respect to time is proportional to, well, let's think. If there is a lot of fire, would you say that causes more fire? Yes or no? Right? More fire cause more fire? Yeah, right? So that's sensible. So the more fire it is, it causes more fire. So it's probably proportional to how much fire there are. Again, this is a toy model. We're just simplifying the problem, right? And just get a sense. But as someone mentioned, I didn't see the name, you cannot burn indefinitely, right? The world is finite, right? The world is finite. So I claim it's also going to be jointly proportional to the total amount of area allowed to be burned that's left yet to be burned. So A minus Y. So Y right here is amount burned, area on fire, and A minus Y is area not yet on fire. Okay? And what is A then? A is therefore the max area to be on fire. Does that make sense? Okay. So what's interesting is that this model models this behavior of something spreading, but there is a maximum. This maximum is A. Because once you have reached A, we have burned everything. And in fact, if you stare at this, there are two equilibrium solutions. What are the two equilibrium solutions? Can you see? Y is equal to what?
0.
0, and also Y equals to what? A, right? This is saying that if there is no fire, then there will never be a fire. And Y equals to A means if everything's burned, they all stay burned. It's gone. They're on fire, right? This model actually is called a logistic model. And it's useful to model things that spreads, model spreading, like perhaps news or rumor or disease, all sorts of things, or even population growth, So this is a pretty good, simple first course model. Now, you also mentioned that are we going to account for the wind and also firefighting efforts? So yes, perhaps if there is firefighting efforts and also the wind, then we may add some correction over here, right? So there may be some correction term to this that causes, that influence the rate of change of how much area is burned, okay? So maybe the wind, right? So there may be a wind factor, and the wind is gonna cause the fire to spread even more, so that could be a plus term over there. But we're also fighting fire with firefighters, so there could be a minus a firefighter fighting efforts, right? So there may be some all of this. possibly in this thing. Now, what's interesting, I'll point out right now, is this. We're going to first consider the situation where there's no wind and there's no firefighting efforts. But the wind can cause more fire to get more fire. But what about firefighting efforts? Firefighting effort is at best constant. Do you see why this is a problem? Because there's only so many firefighters and helicopters and water you can stop an area of water, area by water, a fire, right? Just because there's more fire or less fire, it does not affect how fast you can remove fire. There's only so many people you can use, right? So the firefighting component is actually a constant. And this is gonna be a race between the fire growing, and sometimes there's more fire causing more fire, versus you can only stop fire a fixed constant amount at a time. Of course, if we have a mechanism that improves as there's more fire, maybe that's good, but typically this is a constant. So we're gonna come back to this complication later, but for now, let's just look at the simplified version without wind and fire, okay? Let's look at this version, okay? Let's solve this thing. And what we want to do is that I want to make sense whether these numbers make sense, because you see the data says at noon on Tuesday, it burned 200. At 2 p.m., it burned 300, but by next day noon, it's 10,000. I want to see if this is a sensible number, right? It's like maybe if you're a mayor or if you're the police chief, you want to say, wow, is this just crazy? Are we just doing something wrong? Or is this just naturally going to happen like this, right? Like how reasonable is this number, right? Okay, because it's kind of unbelievable, right? Well, let's try this model, all right? So as a review, would you say this is what order is this differential equation? What would you say? What is the order?
First.
This is a first order differential equation. Do we see? Yeah. What would you say? Would you say this is a linear differential equation? Is this linear?
No.
No, it's not linear, right? The reason why it's not linear is because we are going to have y times y. That's going to give us y squared. In a linear differential equation, we don't have y squared. We may have y second derivative, but not y squared. So this is not linear. But this, we can solve this differential equation using a tool that we have. This is what kind of differential equation? Start with the S. This is separable, right? This is separable. So this is separable. So let's try to solve it using our method of separation of variables. Let's do it. Okay, do it in black. So I separate the variable. I have dy divided by y times a minus y is equal to k dt. Now, here something interesting already happens. We don't know what a is. We don't know what t is. We're going to figure that out later, okay? Let's just solve for this form. So we separated variables, and I integrate both sides, all right? And on the left-hand side, I know that I need to use partial fraction decomposition, so I write little a over y plus little b over big A plus y. Again, big A is the max area of the fire, which we could look at data to figure this out. dy is equal to kt plus c, okay? Now, we don't know what k is, but hopefully the data will help us. First, let's figure out what little a, little b is, and you could use your cover-up method or whatever you like to solve this partial fraction. I don't really mind, so long as it works. A times big A minus y plus by is equal to the constant 1. That's the numerator here. So A times big A minus ay plus by is equal to 1 plus 0y. So we see that A times big A is equal to 1, giving us little a is 1 over big A, and minus AY plus BY equal to 0, that just means minus A plus B is equal to 0. So A is equal to B. So B is equal to 1 over A. What this means is the left side integral turns into 1 over A natural log of absolute value of Y minus, because of chain rule of this minus Y down here, 1 over big A natural log of absolute value A minus Y is equal to KT plus C. The constant integration is already written as this plus C over here. This is very similar to the Y prime equals to Y times 2 minus Y example that we did earlier, right? So hopefully this is not too surprising. That's why I did that one earlier. If we combine this, I'll do it quickly. I multiply A to both sides, and I combine the logs. I have natural log of Y divided by A minus Y is equal to AK plus AC. Now, here we have a bunch of constants multiplied together. Tell me which two I can combine as one constant and which two I should not combine. Should I combine the AK or should I combine the AC?
AC.
The AC, because C is an arbitrary constant. We don't know what it is. So multiplied by A, we still don't know what it is. So I can combine them by abusing a constant. A times K, however, cannot be combined because they are parameters of the problem. A is the actual area that we can burn, and K is some burning rate to which we have yet determined, but hopefully the data will help us determine what that is. So by abusing a constant, this is AKT plus C. Okay. Exponentiating both sides, we get Y over A minus Y in absolute value is equal to E to the AKT plus C, which abusing a constant once more is C e to the AKT, like so. Taking away the absolute value, this is the same thing as before. C times E to the AKT. Again, I abuse the constant once more by absorbing the plus or minus sign into the C. Then I multiply both sides by A minus Y. So I have AC e to the AKT minus CY e to the AKT. And I solve for Y. Again, I cannot combine the AC here because the C are now tied together. So I shouldn't do anything fancy with the C here. But moving the Y over, I get Y finally is equal to AC e to the AKT. Let me write it in the next page. We get Y is equal to AC e to the AKT divided by 1 plus C e to the AKT. All right. And just like earlier, I want to sort of make this look slightly better. So I'll write this as AC over e to the minus AKT plus 1, plus C. There we go. This is the general solution to our differential equation.
Professor, how did you get the last equation again?
How do I get the box?
No, the Y equals AC e to the AKT over 1 plus C e to the
I solve for Y. I solve for Y. You see, I have Y's here, right? I move this term over and I factor the Y out and I divide by 1 plus C times e to the AKT. Do you see that? Yeah. Yeah, this is just algebra, right? So see if you can follow the algebra yourself and get this term that I have. So this is just algebra. Okay. So great, we got this. But now there are some issues. What is A, what is C, and what is K? So for us, we're gonna look up what A is. Let's estimate A. A is the max area, right? The max area to be burned. Now this is a number, this is a physical number. So let's actually look at a map to figure this out. So again, there's nowhere in this differential equation that can tell us this information. So we have to look at something. So let's go to a map. So I'm going to go to my website, my web browser. Okay. So I don't know, map area calculator. Is there such a thing? I'm gonna click this. Okay. Oh, it's already zoomed in on the place that I first looked at this. So look at this area. This is Los Angeles right here. I hope you recognize where you live. And Santa Monica, this is city of Santa Monica right here. The fire is basically this region, maybe above San Vicente right here, right? So this whole area. So how much do we want to burn? That's a better question. Perhaps, zero, right? So how much is there that could be burned, right? So maybe along this beach right here, you know, all the way from here to Topanga Lookout, to over here, maybe hopefully it doesn't cross the 405, maybe go down here. This is the area that's gonna get burned. Okay, that could be burned, right? There's all this grass area right here. Now let's look at the area right here. The area here, it's about 29,387 acres. Let's just round that to 30,000 acres. Okay, so we're gonna use 30,000 as our maximum area, that this is the Palisade fire that could potentially all get destroyed by fire. Okay, so let's go back over here. We estimate 30,000. So roughly 30,000 acres. This we use real data. Estimate. Okay, we use a real data estimate. Okay, that's great. So that means my y function now reads 30,000 times c e to the a, which is, sorry, I have this other one, 30,000 c divided by e to the negative 30,000 kt plus c, right? Okay. Now, what is c and what is k? First of all, c shows up in two places. Because let's think, what if c is 0?
Professor, your voice is freezing. Can you repeat from?
Oh, sorry.
From
Can
the
you hear me
C?
now?
Yes, from
Okay.
the C.
All right. So let's look at this expression right now. What if c is 0? What happens if c is 0? If c is 0, then what can we say about y?
Y is 0.
Y is 0, right? Now, what does y equal to 0 mean in our problem?
It's a stay. Oh no, it's
It means, are there fire? Is there fire?
No, it's 0.
Right. There is no fire, right? This means no fire. But because there is fire, this is not the solution we're gonna look at. Does that make sense? Right? So because there is fire, c is not 0. For our fire problem, the reality, you know, the Palisades, there is fire. So c is not 0. The reason why I'm doing that is that I want to divide top and bottom by c. If it's 0, then I cannot just divide top and bottom by c. And why am I doing this is that I get rid of one of the c's. This is just +1 now. Okay? Does that make sense? Yeah?
Yes.
Now, why am I doing this? Isn't 1 over c worse? Well, guess what? Because c is a constant yet to be determined, 1 over c is also another constant. So that means our solution is really of the form 30,000 divided by some constant e to the negative 30,000 kt plus 1. Again, here we abuse the constant. Okay. So that simplifies our expression. So this is the form of the solution we're looking for. Now, how do I figure out what K is and how do I figure out what C is? That's where our data comes in. So we'll use the data to find K and C. All right. So let's go back to what I wrote earlier. Over here, the initial news of the fire is at noontime, 200 acre burned. At 2 p.m., at 140, but let's say round up to 2 p.m., 300 acres burned. I want to use these two pieces of information to see if having 10,000 acres burned on 12 noon next day is reasonable. Does that make sense? I want to see if I can use this information to predict this outcome. Can we predict this outcome using just this initial information? Because the first-hand information, you see some fire is burning, and then you wait two hours, it's now 300. Can I estimate what will happen a day later? Okay, and using a very simplified model. Does that make sense of what I'm doing right now? Yeah.
Yeah.
Okay. So let's do it. Let's use our form of the solution. The information that's given is at noontime Tuesday, which is, we're going to set t equal to 0 to be noontime Tuesday. And t is in hours. So initially, there is 200 acres burned. And we also have the condition y of 2 hours later is 300. Okay? What we like to do is to figure out what is y of 24. What happens 24 hours later? Is it reasonable that tens of thousands of acres of fire of shrubbery is being burned or acres being burned? Okay, so let's do this. Now this is just plugging numbers to solve for these constants. So let's do that together. Let's see. Y of 0 is 200. I'm going to plug in 0 into this t right here. So that means 30,000 divided by c times, what's e to the 0? E to the 0 is what? E to the 0 is
1.
1, right? Plus 1. This is great because this is saying that c plus 1 is equal to 30,000 divided by 200, which we cancel, it's just 150. So c is equal to 149. Okay, we found c. Now, what about k? We can find k as well. To find k, I will use the other information. Because I already know what c is, I can plug it in to continue our solving for k. So let's use that number. So we know that y of 2 at 2 hours, we have 300 acres burned. That's 30,000 divided by, let's see, c is 149 times e to the negative 30,000 kt. Now what the heck is t? T is 2 plus 1. This is something reasonable that you can certainly solve by hand. This is 149 e to the negative 30,000 times 2k. That's so basically negative 60,000 on top times k. Plus 1 is equal to 30,000 divided by 300, which is equal to 100. So we see that e to the negative 60,000 k, let me just do some math very quickly. I have 100, so that's 99 divided by 149 is this. Again, I'm just doing algebra, nothing sneaky over here. This gives us a k-value, an exact k-value, at least per our model, of natural log of 99 over 149 and divided by negative 60,000. That's our k-value. Okay. So far, so good. Yeah, this is just algebra. I'm sure you can all do it. So we can put everything back into our function. So y of t, which is 30,000, divided by, what was the form of the equation? C times all that, C e to the negative 30,000 kt plus 1. Well, plugging k, the 60,000 and the 30,000, they cancel, the negative sign cancels. So this is just 30,000 divided by, C is 149, e to the 1/2 natural log of 99 over 149 t plus 1. Again, I'm just plugging things in, nothing special. Okay. By the way, do you see how there's an e and there's a log, right? They're inverse of each other, so I can actually cancel them. Well, really, just manipulating the power a little bit. This becomes 149 times 99 over 149, all to the t½ power plus 1. That's because the t½ that's this thing right here, and then e and log, they cancel to be 99 over 149. Algebra, I trust that you can do. All right. This is our function. This is our function. So let's actually plot this. Let's plot this. So remember this equation, all right? I'm gonna plot this. Let's go to my Desmos right here. We have y of t is equal to 30,000 divided by 149 times quantity 99 over 149, all raised to the t½ power, quantity all plus 1. All of this out here, down here, plus 1. Let's plot this. Plot. It doesn't plot because it doesn't understand what t is, so I'm going to change it to x. Oh, why is there no graph? It's because it's so tall. Watch. This is the graph. Do you all see that? Let me change it back to t. I like t better. Does it plot? Yes, it plots. Perfect. So using all of this, we see that this is the curve. So what have we observed? What is the axis on the horizontal axis? This is time in hours. So you see that near initially at 0, it's 200, right? It's 200 right here. 2 hours later, 2 hours later, where is 2 hours? This is 2 hours. It's about 300, right? 24 hours later, where is it? 24 hours. It's about 15,000 acres burned. So you see that. So using this model, I predict 24 hours later, y of 24. Can I apply 24 here? I can't. So I guess I have to use x here. I don't know how I can do that. Why can I not calculate y of 24? Oh well, I'll copy this and I'll put this 24 over here. 24 hours later, it is this number. Let's copy this into our notes. Oh, x equals 24. Oh, it's okay. This is fine. So let me copy this. Oops. Let's go to my notes. Right there. All right, share my screen. You see? Okay. So we saw that y of 24 is roughly 14,265 acres per, which agrees with what is seen, right? Roughly agrees, right? It's in the same order of magnitude. And in fact, if you look at this graph, at some time, it's got cut off, but at some time, it's just gonna approach 30,000 if nothing is taken, no care is taken care, right? So if you look at this again, let me make a better picture. That at hour 60, basically nearly all 30,000 acres will be burned if nothing is done, right? So that's kind of interesting. Questions on this? Yeah, this is interesting.
So the meaning that firefighting just only did a little bit.
A little bit, yes. Yeah. See, this is with no firefighting efforts whatsoever. No firefighting efforts is 14,000. At a day later, it's 10,000. So they did a little bit, but not enough. You see. Now, let's go further. Let's go for. This is not a critique about firefighting, by the way. This is more of just if we believe this model, what will happen? Okay. Now let's go further, and I think this is going to be interesting. Just how much firefighting efforts do we need to stop the fire if we start firefighting from the beginning? Okay. So let me just write in the notes. This number roughly makes sense. Roughly agrees with what is seen. Okay. So this is now part 2 of this fire discussion, which I think it's going to be interesting. How much firefighting is needed to stop the fire if we start firefighting from the beginning? How much firefighting efforts are needed from the beginning? And again, I'm not saying that this model accurately depicts what happens, but this is an estimate and can give an idea. Are needed from the beginning to stop the fire from basically going out of control. That's what's happening right now. So let's look at our differential equation, and we're going to use a tool that you might find surprising. Are you ready? Here we go. What we're going to do is look at our differential equation, dy dt. Again, it's k times y times a minus y. But suppose there's firefighting efforts, right? If there's firefighting efforts, I claim we subtract some amount because that means the rate of fire is being decreased by time, right? So let's say we subtract some number f. Now, why do I say this is a number, a constant? Because the entire world has only so many firefighters, right? So the amount of firefighting effort to stop amount of fire is constant. At least this is my estimate, right? Perhaps there's another mechanism that grows in proportion to how much fire there are, but let's pretend there's only a constant effort of firefighting. Say a constant effort of firefighting. Okay, that is this F right here. This is a constant. how much f do we need? Okay, are you ready? I hope this is gonna be interesting. Okay. So you said, how the heck do we do this, right? Now, you could still solve this by treating f as a number. This is still separable. You can solve all that differential equation if you like, but we don't actually have to. So let's watch. Let's use the phase diagram to do all this. Sorry, I call it phase diagram, but what I meant is phase graph, right? Let's look at the phase graph. If the firefighting efforts is 0, which is the one that we just did, completely no firefighting efforts whatsoever, then we have a phase graph that looks like this. Let me draw it. This is y prime on this axis. This is y. Again, to the right is positive, to the left is negative, up is positive, down is negative. If we don't have any firefighting efforts, y prime is equal to ky times a minus y, right? What does this graph look like? What kind of shape does this make? Can someone tell me what kind of shape is this?
Is
It's
y2.
Parabola, right?
Parabola, yeah.
Right, parabola, right? And just to make sure that parabola, it points in the right direction, let's look at our value k. K is this number. Log of 99 over 149 is negative, but times another negative, that makes it positive. So k is positive, which makes sense. The fire is spreading in a positive amount. So k is positive here. So the y and minus y, that makes it pointing downwards. So we have a curve that looks like this. Okay, this is the phase graph. And this intersection right here, that is A. This intersection is 0. Those are the two equilibrium solutions. And we can assign our arrows on the phase line. The arrows is going to point arrow in the middle like this to the right. On the rightmost is going to point to the left. And on the rightmost, on the leftmost is also going to point to the left. Although those regions are not going to be feasible to us because there is no negative area and there is no area beyond A to be burned. So we really should only be looking at the region from 0 to A anyways. Okay. Now, A is about 30,000. And let's see if this agrees with what happened of what we observed. Initially, how much was burned? Initially, times 0, how much was burned? Where were we? Times 0, what's the acreage?
200.
200, right? So that means initially we start right here. We start somewhere right here, 200. So if there is absolutely no firefighting efforts whatsoever, eventually, what's the eventual fate of all the fire? What's going to happen? Eventually, what's going to happen? Eventually, all 30,000 will be burned, right? Do we all agree? Yeah? Okay. So this is the eventual fate. If y of 0 is equal to 200 and there's absolutely no firefighting efforts, yep, the limit as time t goes to infinity, all of them will be burned. That's expected also within our, it just makes sense. But also makes sense by the phase graph and the phase line. But now let's see, what if there is some firefighting efforts? If we have some positive F. Now, our equation is y prime equals to ky times a minus y minus f. Tell me what's going to happen if I have a graph and I subtract a constant f. What's going to do to that shape? That's going to do what's going to happen?
Go to the 0.
It's going to shift it up and down, right? This minus f, it's going to cause our phase diagram to shift down. So it's still a parabola, but it's now going to look like this. Do you see? It's just shifted down, right? Now here, this is A is right here, and 0 is right here. right? So let's say I shift it down by some f amount, right? So the graph shifted down by f. Now, what will happen in this case? Well, what are the arrows in this situation? Arrow in the middle of the parabola is still pointing to the right, but to the left and to the far right, they're pointing towards, these direction, to the left. So how is the situation different? Well, if we shift the graph down, but if we did not shift the graph down enough so that 200 is still here, whoops. What will happen in this case?
So A is stable.
It still goes to the right, right? Do you see? Now, it still goes to the right, but it doesn't go to A, it goes to this other equilibrium, but it still burned a lot. Do you see that, right? Let's call this A star or something. Okay, so in this situation, if we shifted the graph down by some f, but then the initial 200 is still inside this parabola, it will still go all the way to as far left as possible. Do you see? Sorry, as far right as possible. Do you see? Right? But if we shift down a lot, depending on how much effort that we're putting in, if we shift it down so much, something miraculous happened. 200 is over here. If the graph is shifted down so much so that 200 is in the pointing to the left on the phase line, what will happen? Then that means the fire is just gonna decrease. And because 0 is a natural restriction of our problem, in this case, it's gonna reduce down to 0. Does that make sense? Right? So now we gotta figure out what is the smallest amount of f so that we can make sure that 200 is on the moving to the right, moving to the left region. So what is the smallest f needed? So y of 0 equals to 200 will move to the left. So now that's a geometry question, right? So the perfect situation is if it lands on that intersection, like this. Okay, so this is what we need to solve. A minus y minus f. We need to find a situation, we need to find an f so that at 200, this is 0. Well, that's easy. So let's plug it in. If y is equal to 200, then we get 200 times k times a, which is a minus 200 minus f, and we need that equal to 0 because that is, just at this point, at the horizontal axis. So f, the firefighting efforts, f is equal to, well, this number, 200 times k times a minus 200. That's the minimum amount of f that we need. And we have all these numbers. K is equal to, we calculated earlier, this number, minus 1 over 60,000 times natural log of 99 over 149. And the area A is 30,000. We plug it in and we can find F. So I'm gonna use a calculator to figure this out. So if you use a calculator, okay, do I have a calculator? Use a calculator. Desmos is a calculator. Okay, so I'm gonna use Desmos. So we do 200 times K. I will define what K is. K is equal to -1 over 60,000 natural log of 99 over 149. And A is 30,000. And we want 200 times K times A minus 200. There. 40.6. Roughly 40.6. 44.61. Okay, right here. What does that mean? What does that mean?
The minimum effort.
Right. This is the unit of F. You see, it's the same unit as Y prime. That's acres per hour. What this means is, if in the beginning, firefighter shows up when they first see this fire started and there's already 200 acres that's being burned, if they're able to, from the very beginning, constantly clear out fire at a rate of 40 acres per hour, then this will never spread. In fact, it controls the fire. This is called containment. It contains the fire. It's only going down. There's no going to the right. Does that make sense? So, this is the estimate. That's my proposal. Right. Have we had able to clear out 40 acres of fire, according to our very simplistic model, again, by no means is this ever reflecting necessarily reality, but by this back of the envelope calculation, if you clear 40 acres, probably the fire could be contained per hour, every hour. And it's just a constant effort. Yeah.
What enables us to just say that F is acres per hour just off the bat?
That's because if you look at the units, if you look at our equation where F shows up, F, you see, is in the same line as its Y prime. Do you see that? It's something plus minus F, right? Do you see?
Right, okay, yeah.
So F must have the same units as Y prime. And because Y is acre and the time is in hours, so that's acres per hour. Does that make sense?
Yes, it does. Thank you.
So this is sort of just dimension analysis using that idea. So the units is from dimension analysis. So someone asked, do we have data on the rate of acre controlled? I don't know. I think that data is, I'm sure someone has it, right? So you will have to subpoena them. I'm sure at some point there's gonna be a whole dossier of all of this. But there were a bunch of problems because at the hills, water was very hard to pump up. So there's not enough water pressure to pump up to clear the Palisades, and it just got out of control. And yeah, I don't know. But this is my analysis. Yeah, it did ran out of water. Yeah.
So this gives how many people have to be involved in this effort?
Yeah. Mm-hmm. This means that we need as many people so we can at least clear out 40 acres per hour in the beginning, starting from 2 p.m. Noontime, yes, on Tuesday. If you see it, there's 200 acres on fire. Mobilize everybody. If we can clear 40 acres per hour, then we can control it.
Meaning that 5 hours just only was needed to control 200.
Yeah, but it was not enough. Yeah, it was not enough. Yep.
So this is without involving the wind and other factors?
So yeah, the wind makes it even worse, right? And so the real situation is much worse than this, yeah, because of the wind. So you can add in the wind factor. And in a realistic model of this, then you need to consider the direction of the wind as well and what material is being burned. And because the ember can travel very far, so it becomes a much more sophisticated model. Yeah.
And the material in the direction of the fire as well.
Exactly. So someone asked, what does model this estimate today? So today is what? Today is Thursday, so that is 48 hours later. So we gotta plug in 48 hours. So by this model, if we plug in 48, so I'm gonna need to change this 24 to 48. it will basically be the entire area that was just basically all 29,000, basically 30,000. But because it's not 30,000 right now, that means the firefighting is doing something. Does that make sense? Right. So this model right now is letting it burn uncontrolled, no wind, but also no firefighter. At 48 hours later, all basically 29,700 will all be burned. But
Professor, I have a question about the wind. Like, didn't we include it into the equation because, like, you based your calculations
I
on the
wrote
data?
Right. So I wrote that realistically we should consider the wind, but the wind is a little bit more complicated, so I'm not including that. Yeah.
But I mean, like, we relied on data that was given from like this situation, and it included the wind.
That's true, right? So again, that's why I said this is a toy model, right? This is just a toy model. Yeah. So this is really just because you know when we start, right, you got to start somewhere very basic, right, just to get a sense of what's happening. But yes, you're right. The actual data does have wind, and so if you're realistically a scientist analyzing the problem, or you're part of the team that's solving this and analyzing this, yes, then you need to account that, and then you have to modify everything as well. Then you do need to have that wind as well to make it more accurate. Yeah. But one could safely say probably the situation will probably be worse than what we just predict, even without the wind. Does that make sense? Yeah.
Yeah, I guess it does. Yeah.
Yeah. So this is sort of the base case scenario, right? Sort of the worst case scenario, or rather, we should say a baseline. It could always be worse, and probably the situation is much worse, or depending on what's happened. Yeah. Okay. So anyways, that just yesterday when I was looking at all this, is like, oh wow, this is kind of crazy. But then it does kind of make sense. Like, so for example, right, this number 10. Right? Because I remember on Tuesday I saw, oh, 208, 200. Anyways, any questions on this? Yeah. So someone asked, the units of KY parenthesis A minus will also be in acres. Correct. That's right. Yeah, because it's unit analysis. Okay. So that concludes today's lecture. So hopefully this is kind of an interesting thing to see what we have learned and apply to real, very real world scenario. I'll make up a problem that's similar to this maybe for you to play around. And I'll post the homework maybe later today or tomorrow morning, depending. And we said that we're going to have office hours tomorrow at 8 a.m. I'll send out a Zoom link as well so you can ask questions. Okay.
Professor.
Yeah. All right.
Quick question.
Yeah.
Just to make a comparison to the snowball problem.
Yeah.
Would the dy dt equation be similar to the x prime of t?
Yes. Yeah.
So,
that's right.
Yeah. I think that was the rate of the cleaning, or I don't.
Right. The rate of cleaning. Right. So that one is, what was it? It's x prime, but then it was divided. It was like x prime of t. X prime is equal to like 1 over some linear function, right? It's like 1 over at plus b, right? So that's a different situation.
I'm just trying to see how you I don't know, like how you start the problem. Like
well, in this case, this differential equation is sort of given to you, right? This one right here. So I didn't derive this. I'm just saying that let's consider this model that makes sense, and let's use it to see what kind of answer we get. Does that make sense? Yeah. Right. So to derive this, to justify this, that's a separate work, just like how we did the snowfall one. We did it like that, but this class I will not focus too much on doing that. But I will still show you whenever appropriate. Yeah.
Okay, makes sense.
So you have to be given saying that, hey, suppose using this model, do these predictions for me.
Okay.
Make sense?
So because the snowfall problem was a lot more simpler, we were able to derive.
Correct. We could derive it, yeah, and I showed you, yeah. Oh, so Johan said, you found that 500 acres per hour is a feasible number, right? So, hey, all we needed is 40 per hour. So 500 per hour, right? But then there was some complications, right? Like, you know, the water and then the wind is not allowing these aircrafts to spread water. So yeah. So currently it's a controllable situation, I would say. Yeah, it's probably controllable. Now this is kind of interesting, you know. Being recorded, but I was reading about, you know, like fire dynamics and modeling, just like some documents on all of this, and there are arguments about using mathematical model to sort of analyze all these situations, because you say, well, now the model says this, but you can always change your model to say different things. That's not untrue, right? But you know, quite often this is used in a situation where there's a court and there's a judge saying that, all right, the people messed up, right? And who's to blame? And, you know, if this is the expert witness and you came up with, well, you know, we could have just used 40 acres per hour to fight the fire, and we could have done 500, so someone should be blamed, then someone get into trouble. So that's the danger of using these information, I would just say, right? We're just doing a fun calculation just to see, you know, what could happen, yeah, or what did happen. That's all.
Professor, I have a question from the homework, if you wouldn't mind after to disconnect this record.
Sure, yeah. I could just continue recording and
okay.
And then yeah, so just to answer your question.
Professor, homework for which one the name of the beast is to the name of the beast.
Yeah.
Question 4. Actually, I applied too much time, but I didn't get, just only I found 4. I didn't get the...
Question 4, let me take a look.
Yes, Professor.
Let me see. I don't even remember what I gave, so let me look at it.
Okay, thank you.
So...
It's supposed to have 5 parts correct, but just only, I have 4 parts, you know. Is multiple parts.
Okay, let me share my screen. This problem?
Yes.
Okay. So you're given that y equals a sine is a solution to this, right?
Yes.
And so that means, well, first of all, we should plug it in and to see what we get. So on the left side, if you plug in sine into dy dx, what do you get? What is the derivative of sine?
Is cosine.
It's cosine. But the right side is kind of interesting. 1 minus y squared, 1 minus sine squared is cosine squared. And then when you take the square root, that becomes what?
Positive, negative, positive cosine.
Well, no, that's not what it is. You're close, you're close. So this is...
the meaning that just only we have to use positive.
Right, meaning
because
absolute
it's
value.
Under the
it's
square
absolute value. It's absolute value.
Absolute
Yeah.
value.
Right. So let me copy this question onto my notes. So I won't solve this completely, but I will show you what is it that you need to do, okay? Or think about. So here we have y prime is equal to cosine of x, and square root of 1 minus y squared, that is square root of cosine square x, that is equal to absolute value of cosine of x. That means, right, because square root of anything squared is always the absolute value. Okay. Now we want to know which one could be an interval of definition. That means we need to know when is cosine of x equal to absolute value of cosine of x. What I would ask you to do is think about their graphs. So I'm going to sketch out what cosine looks like. Cosine looks something like this, right? This is cosine. What does absolute value of cosine look like? All the negative parts turns into positive, right? So absolute value of cosine of x looks something like this. Does that make sense?
Yeah. Yes.
So now what you want to know or want to figure out is on what interval is this orange? I don't know what color this is. Is the orange curve equal to the blue curve? That's what you need to know, right? That's when they're actually equal, right? So for example, this interval right here will not be an interval definition because here, those two functions, absolute value cosine and cosine, are not the same.
So 0 to pi 4, pi 2.
Yeah, so you got to figure out which interval. And then that's the challenge right here. Make sense? So there could be many answers. I hope I designed this correctly. Yeah.
So I have 0, 1. Let me check my answer. I have 0, 1. I have 99 pi over 2 and to 101 pi over 2. I have 4 pi and no pi over 2 and negative pi over 2 and 0 and 0 and 1 as well. Just only 4 parts.
So I don't know how many there are, but you got to find all of them.
It has to be 5, professor, you know. I check all of them actually, one by one, but I didn't get one of the best benefit of multiple choice, you know.
Okay, I'm sure there's a way to figure that out, but I want you to think about this carefully and think about this graph, and we're just asking on what interval are these two curves equal. That's all. You can do it. You can do it. Yeah, I'm sure you can.
Professor, I tried, but I think one miss has to be missing here because I tried maybe 12 times, but I couldn't find the 5.
Do it again. Do it again. I'll check later on, but right now this is my suggestion to you. I'm sure it's there. I hope it's there. Maybe I made a mistake, but then I hope it's there. Okay.
Okay. Thank you.
Yeah.
Thank you.
Yeah. I think people were able to. I know it's annoying, but frustration. Trust me. You know, I'm not trying to torture you all, but that work, it's gonna help you. That's all. It's gonna
actually, I asked from another student and he told me I found 4 as well. You know.
Yeah. So they're missing one. Yeah. So I think someone in the chat says there's missing one. Try double checking again. It's there. Okay.
Oh,
and
okay. Thank you.
You can do it. You're on the right track. You're on the right track. Keep going. You got this.
Thank you so much, Professor.
Mm-hmm.
See you tomorrow.
All right. I'll see you all tomorrow in office hour if you choose to come at 8 a.m. I'll also record that just in case. Okay.
Thank you.
All right. Let me stop. Do I stop? Share.